Okay, so predicting equilibrium concentrations. What is the big to-do? Well, the big to-do is everything is always trying to reach equilibrium, right? I mean, that's just nature. Nature is just after getting equilibrium. That's all it does. The balls roll down hills, chemical reactions try to get to equilibrium. Just what is equilibrium and what is it good for? Well, if you know the equilibrium composition, I mean, that's really what you're after. Whether you're making potato chips or trying to make some drugs or monitoring what's going on inside plants, I mean, equilibrium compositions is really, that's always what you're interested in. So how do you know when you're at equilibrium? Let's get some help. Oh, wow. Alyssa and Ramiro, come on up, please. Okay. Alyssa doesn't. Okay, Alyssa is the reverse reaction. So I have reaction A going to reaction B. Or sorry, reactant A going to product B, right? So remember, you're on this side. So this is the beginning of the reaction. We have all what? Compound. We're all reactant. It's all A, right? So the height is pretty much the concentration, right? The higher the height, the more stuff you have. So here's our forward reaction and our reverse reaction. Okay? The idea that we're going to try to bring across is things are dynamic. So you have to do it at the same time, even though unless you're not going to get anything, just make the motion. All right? So at the same time, yeah, go ahead. Scoop and dump. All right? Yeah, and then dump. No, in there, right? Forward reaction. There you go. Okay, keep going. All right. Okay, now try not to make this work. Don't scoop, just straight down. All right, just straight down. All right, so there's a forward reaction, there's a reverse reaction. All right, keep going. So are they at equilibrium? How can you tell when they're at equilibrium? When they're the same heights? All right? Because if it's the same heights, what you're saying then is that every single reaction is at equilibrium when you have equal amounts of reactants and products. That doesn't make sense, right? Some reactants are going to make a lot of products. Some reactions aren't going to make hardly any product, right? So all that really matters here. Keep doing. Keep going. Guys, go faster. Go faster. All right? All that really matters is what? The amount that's being transferred into the two containers, right? As long as the overall amount of A doesn't change over time, the overall amount of B doesn't change over time, that's when you're at equilibrium. So when this little height isn't changing, or you could say concentration, right? Same thing. And why is there ending up to be more B? Because look at his beaker, right? That's all that matters. I could have given the big beaker to Alyssa. Then there would have been more reactants at equilibrium, right? So really this is just reaction rates is all we're messing with. So I don't even think the heights are really changing anymore. But scoop it up and hold it up. Don't dump, hold it up. All right? The volume in here is probably really close to the volume in Alyssa's. So thank you very much. Now I don't have paper towels. Just wipe it on Romero's dirty. All right, thank you very much. So that's the idea of equilibria. They're dynamic. They're going both ways. Okay, so that's kind of what this is all about. What does dynamic equilibrium refer to, and how do you represent it? Well, you represent it with this double arrow. Whoop. That's how you represent dynamic equilibria. Reactants going forward, products going backwards, forming reactants. Okay? When is equilibrium reached? When what's not changing anymore? Yeah, well, height in this, but for reactions it would be concentrations. Yeah, of anything, of everything. The concentrations of everything have to stay constant. Even though you have this dynamic equilibrium going on, it's just, the concentrations aren't changing. Okay, so how do we get around to predicting the amounts at equilibrium? Well, that's kind of the big goal for today. The only thing that's going to help us out is to write an equilibrium constant expression. Because if the amounts of products and reactants aren't changing over time, Well, heck, you can just divide them out and you should get the same number all the time. You just have to stick and have some rules to doing this, and everyone does it the same, so everyone gets the same number. Because the reaction, right, the concentrations aren't changing. So how do you write this equilibrium constant expression? Well, you're supposed to write Kc, right? And then you put all the what on top and all the what on the bottom. All the products. Now, you're supposed to write it in brackets, though. Because the brackets mean what? Concentration. Do you know what concentration units they're going to want? Big M, molarity, right? Remember what big M was? Brandy, what was big M? Yeah, it was big M. It was molarity, but it was really what over what? Moles of solute over liters of solution. Exactly. Okay. So that you might need that coming up. But what is never included in an equilibrium constant expression? So you have this reaction, right? All these reactants. And then all these products. Here, I'll take it. Then all these products. Okay? Some reactants and some products, they never show up. Eric, what's the trick to doing that? How do you identify, I'm not supposed to put him in the equilibrium constant expression?
They show up in a product and reactant set?
No. Well, if they did, they would cancel. You're right in that sense. Here's an example of one. H2O with little subscript L. The reason, and because if you put this in the equilibrium constant expression in brackets, right? If it was in a reaction, so that means you got to you put it in the brackets, right? Well, you should really erase that. Google it. 55.4 molar. All pure liquids have some molarity. They have some concentration, moles over liters. It's a pure liquid. Same thing with a solid. There's so many moles over the volume. They're just numbers. So you don't want to do that, do you? I don't, right? So let's just forget about it. They're constants. They're really going to get put in with the big K. Let's not even worry about them. Pure solids, pure liquids, don't write them in an equilibrium constant expression. If everyone does that, we'll be... Let's try a few. How about this first one? Vanessa. Okay, I'll get you started. Kc equals something over something. What would you write? Products over reactants. So in brackets you'd put the top CaCl2. Yep. And on the bottom Ca plus 2. Yep. And Cl minus. Okay, now is it plus Cl minus or times Cl minus? It's times. Okay. Now, what do we do with this plus 2 charge? Do we do anything with it? It's nothing. It's just calcium plus 2. That's what it is. So it's important that you write it. What about that 2 in front of the chloride? Yeah, you got to put it up here. All those stoichiometric coefficients become powers. Right. Regardless of what they are, they become a power. Okay. Let's try, let's jump down to D. That's about as ugly as it's going to get. Kc is products over reactants. Mari? Yeah. What would you write on top? Cl bracket, it's concentration. Little 2, square it. Careful. It has a little. All right. Little L's and little what's? S's. Disregard, right? Because they're going to be pure liquids and pure solids. Okay, so you can write a 1 or something, but who cares? Okay, what would you put on the bottom? Let's pick on Jessica. What would you put on the bottom? Yeah. And square it. All right? How about the other guy? Yeah, bracket Cl2. Gases can have a molarity. There's dissolve. Okay. So that's writing Kc expressions. Products over reactants, raise them to their stoichiometric powers. B? Oh, what would you put on top? Put a 1 up there. Exactly. Good question. Calcium and chloride squared. Good question. Okay. Now let's get into the meat of this stuff. The meat was, okay, since everything's at equilibrium, how do you figure out what are the amounts at equilibrium? That's the big goal. So I say do it by making an ice table under the reaction. Okay. So all these questions, there's a lot of verbiage in there. They tell you the amounts that are initially present and stuff like that. So the point is, make a nice table. Okay? Because look how it says how many moles of A and B are present at equilibrium. So that's when you do this ice stuff. You want to figure out, okay, just how much is at equilibrium of reactants and products. Make an ice table. Okay, Alyssa, well, she's not here. Cassandra, it sounds all nice. An ice table. What does the ICE probably stand for? I for anybody? Starts with an I. Initial. Right. Okay. How about the C? Not concentration. Starts with the C. Change. E. This one you can get. Starts with an E. Equilibrium. Okay. So, initial. Our initial row. We have to put in all the initial amounts. So, Albert, what's there initially for A, B, and C? What would you say? Two for A? 2 for A. Oh, that's a stoichiometric coefficient. So down here, up in the reading, it says 8 for A. Okay, now let me try to confuse Albert a little bit. Is it that simple? You got that 2A there. Don't you want to say 16 or 4 or something?
8 squared.
Or 8 squared? All right. It's because the initial row is just the initial amount of A, B, and C. Well, the initial amount is 8. So it's just 8. Oh, yeah, we're going to use the 2 for something else. Ah, sorry. He's fine. Right? He's 8. The B initial amount is 6. The C initial amount. It doesn't say. What is this 6 doing? Is that initial? No. So don't go writing him. It doesn't say. If it doesn't say, it's going to be 0. So you can write 0 or a dash, whichever one. All right? Change. Now this is when we use those stoichiometric coefficients. But when there's a problem and you don't know, there's an unknown, usually what symbol do we use, Victoria, for the unknown? You write the letter X, right? That's Victoria, right? Don't we use X? Or do you want to use something else? Let's use X. That's the book uses. We always use X when we don't know what something is. So we're going to use X for the change. So you put it in there. Except you need to be a little more specific. This change, in order for the math to make it a lot easier, is the change going to be negative or positive for the reactants? In other words, is the amount of reactants going down or is it going up? Right? Because you start out like this. All right? Is the amount of reactant going down or up? It's going down. So that change should be negative. So for the reactants, you always write negative X's. Products, positive X's. Now, we're not quite there yet. Look how, if B reacts, B disappeared, or sorry, A disappears twice as fast as B. Notice that? C is forming 3 times as fast as B reacts. So you have to take into account those stoichiometric coefficients. How do you do it? Did anyone see it? Just put those stoichiometric coefficients where? In front of the x. Whatever it is, put it in front of the x. You have 2a, so it would be 2x. Well, negative 2x technically. And b, so just negative x. But c, you'd have to put 3x. Okay. Now, this next part, there's so many different ways that they can ask these questions. There's several different permutations. I just say always approach all these the exact same way and do just what we did. You write in the initial amounts. You figure out the changes by writing in negative x's and positive x's and using the stoichiometric coefficients. And then to get the equilibrium row, just add up what? Whatever we had initially and the change. Right? So this would be 8 minus 2x, 6 minus x, and 3x. Okay. Does that make sense? Here are all of your answers. Right? For the equilibrium composition or the amounts of reactants and products at equilibrium, whatever. That's your E row. Those are all of our answers. So all we got to do is figure out what x is. In this case, how are you going to figure out the x? Plug in the 6 for what? 6 moles of carbon are found at equilibrium. They told you the answer for carbon, so 3x has to be 6. Right? This guy, whatever you wrote for under the carbon, he has to be 6. So 3x has to be 6. X is 2. Right? So how many moles of A and B are also present at equilibrium? Well, moles of A, that's just 8 minus 2x. Moles of B, 6 minus x. So let's see. 2 times 2 is 4. That would be 4. Well, they're both 4, it turns out. Right? It doesn't have to be. That's just how it turned out. So you end up with 4 moles of A and 4 moles of B. So does that make sense? When they want to know the amounts at equilibrium, they can call it equilibrium composition. They can call it whatever they want. When you want to know the amounts of reactants and products at equilibrium, ice table. Okay. Let's not do this. Let's just ask Ramiro if this is an ice problem. Is this an ice problem? Do I have to make an ice table? Yeah. Look at that. What is the equilibrium composition? Exact same thing we just did. Let's jump down to the next one. Summer. Is this an ice table? Yeah. What is the equilibrium composition again? Right? Man, well, we'll jump up and do some more of those. But let's jump into something more, right? Because homework can't all be that straightforward, right? So let's try one of these. Okay. Lauren. Is this an ice problem? Before you answer yes or no, what are you supposed to be looking for? Ice only is only for what type of question? Equilibrium composition. And they're not always going to use the word equilibrium composition. They're going to use the word, how much of B is at equilibrium? How much of C is at equilibrium? You want to know the amount or the amounts at equilibrium. That's ice. So do you want to know, is this ice? No. They want to know what? Kc. They want to know what Kc is. Up to this point, Caroline, in this Chem 1402, General Chemistry 2, all through Exam 1, when we wanted to know something, we just dug up the equation and did plug and chug, right? Not the case for this. How are you going to do it? For this type of question, where are we? You have to write your own equation, right? You have to write what Kc is. So you have to write the equation. Where are we? So Monica, what's the equation? Okay, well, let me slow down here. Kc is equal to what? PCl5 in brackets though, right? Okay. Over PCl3 brackets times chlorines in brackets. That's our equation. Eric, our equation has what? 1, 2, 3, 4 variables. They had to have told us 3. What are you going to do? Okay, moles. It's close. You have to get molarity. That little c means molarity, means concentration, but in molarity units. Now, what was molarity? Moles over liters. Big M was moles over liters. So let's find PCl5. Moles over liters. Let's find PCl3. Moles over liters. Let's find chlorine. Moles over liters. Brandy, is it going to be the same liters in all these? Yeah, because it's all the same container. Did they have the nice units for us? Yeah, they did. That's nice. Do they have the mass and the nice units for you? It's in moles. It's not in grams, so that's nice. Right. So this question could have been made much more difficult. Have the liters and milliliters, and then have the grams of each one. Probably would have been a better question, but that's okay. Okay. Let's get it. Yeah. Look at this. Then that's why I like. Do you hear Jessica's question? Does the temperature matter? If you follow the logic of it, they ask for Kc, so you write an expression for Kc. If it's not one of these 1, 2, 3, 4 variables here, you don't care, right? They can give you all the extra information they want. All you care about is that equation that you wrote. So see if you can get this to work. Get the concentration of phosphorus pentachloride, trichloride, and the dichlorine. Plug them in and see what you get for Kc. No, you don't assume. They are. MOL. Right? Yeah, they all say MOL. Oh, 0.0126. Oh, I see what you're saying. Yeah, that 0.01, they're all, yeah, they're moles. Phosphorus pentachloride is 0.0126. Oh, 0.17 chlorine. Phosphorus trichloride. Did I? Oh, shoot, did I? Shoot. It's 0.0148. Thank you. Ugh. PCl3. This guy's wrong, man. I don't know. Hopefully I did this right. If I took 3.15 times 10 to the negative 3, divide it by 0.0037, or 3.7 times 10 to the negative 3, then divide it by 0.02175, I got about 39.1. Oh, good deal. Okay. So you should get that to work on the calculator.
Do we just put the number, do we put that?
Oh, are there units? Is that what you're asking, Summer? Okay, good question. It looks like the units don't all cancel here. To answer your question on units is a General Chemistry 3 question. Now, where's General Chemistry 3? It's better known as Analytical Chemistry. And because what's going on is we're not telling you the whole truth here. That this is good for giving you rough answers, but it's not going to be perfect. If you want to give someone a dosage, this is close, but you're going to make some modifications, and you're going to see that there really aren't any units, equilibrium constants. And I call it General Chemistry 3 because if a lot of folks if you're like a biology major, or you're minoring in chemistry, a lot of folks push off analytical chemistry to their senior year, and it's really hard because you don't remember any of your general chemistry. That's why I call analytical General Chemistry 3. So if you can squeeze it in, I'd just get it over with if I were you. Otherwise, good luck trying to remember all this stuff. Okay. So we're okay with a 39.1? No units. Analytical chemistry. That's every fall semester. You need that for your minor. Okay, let's see. Let's ask Maria. How would you write the equilibrium constant expression for the following reaction? What would you write? Kc equals bracket CO2. Okay, don't give me the bottom part. I'll ask somebody else here. Vanessa, the bottom part.
The bottom part?
Yeah.
Oh, okay. SO2.
SO2.
SO2 brackets, and then O2.
O2 brackets.
And then 1.5 on top.
There you go. Whatever that stoichiometric coefficient is, you just make it a power. What is a half, by the way, as a power? Does anybody know? Better known as square root. 1/3 is cube root. Okay. Let's see. Let's try, yeah, these are all, okay. Let's try this. Try this one. See if Mari can give us some guidance, though. I don't know if you had a chance to read the question yet. Have you? Oh, you have? Okay. Is this one of those ice problems, or is this something else? Why is it ice? Yeah, the very last sentence there. Kind of reworded it, but yeah, they're after, at equilibrium, how much do you have of everything? So it is. It's an ice problem. See if you can knock it out. If you're stuck, now's a great time to ask. No, you want everything to stay in moles. Yeah, you want everything to stay in moles. Another thing that this is called is a mole table. Yeah, you don't want to put it into grams because grams don't have the whole number ratios that moles do. That would screw everything up if you converted everything to grams. It's a good question. What to do? Yeah, if they didn't say any initial amount, give it 0. The equilibrium mixture contains this, so that's not initial. Alright, so there's no initial NOBR. You just have to write 0 here. Right? See this guy? It gives an equilibrium mixture containing this. So that's initial for this. Sorry, that's not initial for this. That's equilibrium. So yeah, for that NOBR is none. That should be a 0. So that's how I filled out my initial row. Hopefully yours matches. You have to divide by 2 to get it. This is 0.03. That you messed up. No, you messed up. Did it work?
Once you get this, you set it to 2.
You have to set it equal to... Okay, so here's all your answers, right? And once you get x, you know the equilibrium amounts of all these guys. This guy will be 2x, right? They told us what this one was. They said it was 0.0311. So this has to equal 0.0311. That's how you solve for your x. Yeah, so set him equal to 0.031, get your x, then substitute everything in. Yeah. Okay, so I think everyone's got this here. Okay. So that 2x has to be 0.0311. So then if you do your math, .0311 has to be 2x. What's x then? Wow. Carolyn, what did you get for your x? 0.0155. Okay. So then my moles of NO, my moles of Br2. What did you get for your moles of NO? Jessica, what did you get for your moles of NO? 0.02. Did anybody else get that? Okay. Moles of NO. The Br2? Alyssa, what did you get for the BR2? 0.0107. Does that sound good?
Yeah.
All right. I don't want you to lose any points here, so let's finish this. The moles of NOBR. What would you put for that? Is it the 0.0155 or the 0.0311? That's the 0.0311. All right, because that's the equilibrium amount. So those are all my answers. All right?
So you drop the twos, like 2NO and 2NO.
Well, the 2 was used. It was used in the 2x. It's pretty much the only place it's used is in the change row, right? To get the equilibrium row, you just add the 2 rows up. Let's try this one. Follow the same game plan, right? What's the composition of the final reaction mixture? So you know it's going to be an ice problem. Follow the same game plan. Only plug in the table what's provided, what's being asked for. They didn't say anything about chlorine, right? Yeah, so you have to put 0.
So the value is just going to be x.
Yeah, it'll just be 0 plus x, yeah. Yeah, keep going. So now I just add this plus that, and you get this. This plus that, you get this. This plus that, and you get this one. Minus x, yeah. You just go fill it out first, then you'll see. Oh, hold it. We didn't read this careful, right? To give. So that means this isn't an initial amount.
So it goes right here?
No, if there's no initial amount given, what are you supposed to put up here?
No.
0. All right. Oh, you did the same thing, AJ. All right. Let's make sure. Okay. We did an initial, This is where you gotta read these things slowly. I even screwed up reading this too. Okay, the 2.5 goes where? Phosphorus pentachloride, right? Because that's very clear that that's the initial. Okay, I don't see moles. I don't see moles. Here I finally see moles. But it says to give, and then it says at equilibrium. So you're not using this number for an initial. So and since they didn't say, everything has to be 0. Right? That's your initial row. They didn't say. Keep going. It should work. And then write out the initial mole. Sorry, write out the equilibrium moles of everything once you finally get everything to work out. That's technically supposed to be a positive x, but it really doesn't matter. You end up with x and x, right? Yeah. See, they're both x, so it really doesn't matter. Now these are minus x's, these are plus x's. This is reacting, that's forming. So reactants are always negative x, products are always positive x. Yeah, so you have 2.5 minus x, and then so you just end up with x and x. That's good. So Alyssa, what did you put in your change row? Yeah. And then your equilibrium row, Cassandra? Oh no, just this row. How'd you get that? Yeah? You just remember you just add this guy up with this guy and you get him. So it'd be what then? 2.5 minus x, and keep going. Just x and just x. Okay. And then hopefully what did you do next, Albert? Yeah, I kind of knocked it out of there. For which one? For the PCl3. Ooh, nice, because there's no math, right? That has to be my x. Well, now we know what chlorine is right away. Chlorine has to be 0.338 moles. PCl3 has to be 0.338 moles. The only one left is PCl5. What does it come out to be? 2.112. Not so bad. There's all your answers. All right? So we skipped some problems, but I think you have the idea, don't you? There's either going to end up writing a Kc expression pretty much, or find equilibrium amounts. If it is, make an ice table. Okay? So we have lab tomorrow. You can come by tomorrow if you want in lab and ask some questions if you have some questions.